by a buoy, yes, by a buoy at the top. Over a length of 350 meters, it is equipped with 25 triplets of photomultiplier tubes. Wow. Over a length of 350 meters, it is equipped with 25 triplets of photomultiplier tubes, building a three-dimensional array of 885 PMTs in total. The instrument volume of ANTARES, the instrument volume of ANTARES is 0.02 kilometers cubed. So it is not as big as IceCube, which is fine. It's a complementary experiment. Not every experiment is going to be the same and, identical as other ones, right? It's still important. Even if your effort is smaller, it's still important because it's important to get data from multiple sources and multiple ways and multiple types of detectors. And Antares is in the northern hemisphere, so it sees the northern sky. It will have other types of noise, other types of problems, and it's very, very good to have multiple types of detectors and multiple types of people working on these multiple types of detectors so that you're bias free as much as possible, and you also get information from multiple different sources. So even though Antares is a smaller effort, it's still very important. Complementing IceCube is very important. IceCube and Antares are both optimized for the detection of muons from charged current interactions of high energy astrophysical neutrinos. So basically they're looking for the muons that will be formed when high energy astrophysical neutrinos interact with the medium and make the secondary particle, which is the muon. So this thesis is a particle astrophysics thesis, right? So it will be very common that particle physics stuff will come up. Even though our motivation here is astrophysics and understanding astrophysics, you have to understand that the way we're going about it is through particle physics. So if you like particle physics, this is going to be a lot of fun. But if you're thinking that, oh my God, I don't care about particle physics, I am going to just warn you now that there's going to be particle physics coming up randomly all the time, because our detection method is not traditional astronomy, right? Our detection method is particles, and we want to see a specific particle, and there is a plan for that, and there is generally a particular signature or a particular interaction we're trying to capture or detect or measure on. And oftentimes particle physics is like a jungle of particles, right? It can be a little confusing. Like you might be like, what are you talking about? Why do you care about muons? It's because the neutrino, it's just this small particle. It's going to interact with the there was a noise. When it hits the Earth, it's not going to give us a lot of time and write us a letter about, hey, I've hit the Earth, can you measure me? It's going to be very fast, and it's going to quickly turn into other things when it does hit us, when it does hit the Earth, whether that's the Mediterranean Sea in Antares or the ice in IceCube. And we have to be ready to pick up on the interaction that it does in the medium. So you'll notice that a lot of these neutrino detectors, the detection medium is something like ice or water or salt or whatever. And we want to instrument the detection medium because as soon as the neutrino interacts, it does something. The something will be different for different experiments, but whatever that something is, we want to detect it and be ready with our instrument to pick up on that particular signature. And in the case of these optical detectors like IceCube and Antares, they're both optimized for the detection of muons. Muon is another type of lepton. It's also part of the lepton family. And it's a secondary particle that is made from what we call charged current interactions of high energy astrophysical neutrinos. I'll show you the interaction in just a second here. But IceCube uses the Antarctic ice as a target medium.